In this video, we'll take a look at exponential functions and their graphs. Specifically, we will learn how to evaluate exponential functions by hand and on our calculator, and sketch the graph of an exponential function. First, before we talk about exponential functions, exponential growth, we want to know the difference between exponential growth, which refers to the original value from the range that increases by a percentage, the same percentage, over equal increments found in the domain, and linear growth, which refers to the original value from the range increasing by the same amount over equal increments found in the domain. So let's take a look at these first two examples. We have two sets of ordered pairs, really. We have x values and f of x values. And we notice that in the first example, x increases by 1 every time. And I think you can see fairly easily that if we add 30 each time, subtract 30 each time, and then we subtract 30 again, and then we subtract 30 again, we get the f of x, or the y values. That means that this graph is, or this function is linear. And it turns out our slope is negative 30. For the second example, we notice that our x values increase by the same increment, just 1. And if we tried to say, well, if I do 70 and subtract 49, that we get minus 21. So if I subtracted 21, but then if I subtracted 21 again, I wouldn't get the 34.3. So what we notice here is that if I divide, in this case, I divided 49 by 70. So 49 divided by 70 was 0.7. 34.3 divided by the 49 was 0.7. 24.01 divided by the 34.3 was also 0.7. And in this case, what we're saying is if we multiply 70 times 0.7, we'll get 49. Multiply by 0.7. So each one is essentially 70% of the previous one. This one is exponential, and our growth factor, well, in this case it's actually a decay factor because it's less than 1, is 0.7. So it's actually a decay factor because it's less than 1, and we'll talk about that a little bit further in the next couple of examples. All right, so let's take a look at an exponential function. An exponential function is going to have the form f of x equals ab to the x. A has to be a non-zero number, and it's always going to be our initial value. You can see that because if x is 0, f of 0 would be a b to the 0, and of course b to the 0 is 1. So we would get f of 0 is a. So that also tells us that we're going to have the ordered pair 0, a. B has to be a positive real number, and it cannot equal 1. If it were 1, this would be kind of a boring function because we would raise 1 to the second. It would be 1, and 1 to the 7th would be 1. So it wouldn't be exponential. The domain is all real numbers. And notice here that the range changes if a is positive or a is negative. So let me give you a quick sketch of these two. If a is positive, our graph is going to look like this, and everything is going to be positive. But if a is negative, so this is a greater than 0, if a is less than 0, in other words, it's negative, then our graph is going to look like this. So notice that the range would be all negative real numbers in this case and positive real numbers in the second case. And of course, the y-intercept is 0a, and we are always going to have a horizontal asymptote of y is equal to 0. So we'll notice we have that horizontal asymptote here, and we also have that horizontal asymptote here. So what I'd like to do is take a look at a function, f of x equals 2 to the x, and consider just a table of values. So we do have to kind of remember some of our rules of exponents. So if x is 0, 2 to the 0 is 1. If x is 1, 2 to the first is 2, and 2 squared is 4. What does it mean if we choose negative 1? Well, if you remember, that makes that into a fraction, and that would be 1/2, and negative 2 would be 1/4. So if we look at the next page, I've graphed those points here. I actually have a few extras as well. And this is the exponential growth function. In this particular case, a, b to the x, our a is just 1. Our b is 2, and of course our variable is x. So in this case, our initial value is 1, and you'll notice we do go through the point 0, 1. Notice that this b value here is greater than 1. And in that case, our graph, our exponential graph, is going to be increasing. In other words, it's going up from left to right. So it's interesting to know, what does that look like if our base, our b value, so in this case g of x equals 1, 1/2 to the x, our b value here is less than 1 but still positive, greater than 0. And you can make your same table of values here. Notice that when you plug in the same numbers, if I plug in a 0, 1/2 to the 0 is 1. 1/2 to the first is a half. To the second is a quarter. If I do 1/2 to the negative 1, that takes the reciprocal and we get 2. And then 1/2 to the negative 2 is going to give us 4. So again, we have graphed this here, and what you should notice is that if our b value is less than 1, this graph is actually going to be decreasing from left to right. Okay, so let's take a look at two different functions here. We've got f of x equals 3 to the x, and g of x equals 1/3 to the x. So in this particular case, our base b is greater than 1, so we know it's going to be increasing. It's going to go through the point 0, 1, because 3 to the 0 is 1, and 3 to the first is going to give me 3. We also know that this horizontal line, the x-axis, is our asymptote, so we won't go below that. When we look at the second one here, we notice that our b value is less than 1, so this is going to be a decreasing function. Our a value is 1, so we'll have 0, 1. G of 1 would be 1/3, and g of negative 1 would be 3. And so we get this decreasing function. It's going to get closer and closer to this axis here. So for this first one, 3 to the x, the domain is all real numbers. The range is 0 to infinity. Notice that we do not include the 0 because it's an asymptote. And our horizontal asymptote is y equals 0. Similarly, for the other one, our domain is still all real numbers. The range is 0 to infinity, and our horizontal asymptote is still at the origin, y equals 0. So just like all of our other graphs, once we learn what a graph looks like, we can shift our graph around. So if we have something of the form a times b to the x minus h plus k, the a is going to be what we call a stretch factor. The h is our horizontal shift. Notice if we have minus h, it's to the right. And if we have plus h, it's to the left, kind of opposite of what you would think. And k is going to be a vertical shift up or down. If we wanted to reflect it across the y-axis, then we would have to put a negative sign in front of the x. So let me show you that, and we've actually just seen it above. When I have f of x equals 3 to the x, we know that graph is increasing. If I say f of x equals 3 to the negative x, another way I could write that is 3 to the negative 1 to the x, or alternately 1/3 to the x. And that graph is just a reflection across the y-axis of the previous graph. So keep that in mind. Remember that your horizontal asymptote is always going to be y equals k. Your domain is the all real numbers, and your range is going to vary based on any vertical shifts up or down. So let's just look at a couple of examples here. If we have the graph of 2 to the x, we should know that that goes through the point 0, 1, 1, 2, and that it is increasing because the base here is bigger than 1. If we have 2x minus 2, this should be shifted to the right 2 units. So that graph might look like, instead of 0, 1, it might be at 2, 1 and 3, 2, and would have the same shape. It would just be shifted to the right. In the next example, we have the same 2 to the x that we drew up here, only we're going to shift it down 4. So now our asymptote gets shifted as well. And so we're going to have the points 0, -3, and 1, -2. So 2 times 1 minus 4 is -2, and we know that it's increasing still. For our last example, we have minus 2 to the x. Now notice we didn't put the negative in front of the x, we put it in front of the 2. So in this case, it's going to be a reflection on the x-axis. So we've got our 2 to the x. This will be 0, -1, and 1, -2, and it will look like this. Again, we still have that same asymptote here at 0, so we're not going to cross that. It's just that reflection across the x-axis. The last thing in this section would just be, how do we evaluate something using our calculator? Something that has that exponential. So we have two ways really to do this, but in general, you want to be able to use the caret key. And the caret key looks just like this, meaning raise something to a power. And it is directly above the division key. So if you see the division key, you'll see that caret key above there. So if we wanted to evaluate this function, we would literally type 8 parentheses 1.2 end parentheses caret, because we're going to raise that 1.2 to a power, and then we have to put this in parentheses as well. Otherwise, we'll raise it to the 5 and, raise it to the x and then subtract 5, and we want to raise it to that whole power. So we can do 1.2, and we've got 3 minus 5, or 8 times 1.2 caret squared. So I get approximately 5.56. But any time that we can give an exact answer we want to, so if you use your calculator and use the math frac option, you will get 50/9. We're going to leave exponential growth for another video. Thank you for listening.